In this section, we're going to talk about, well, in this video, we're going to talk about section 4.2, dealing with prime and composite numbers. And in this video, we'll recognize prime and composite numbers, determine whether a number is prime or composite, then determine the number of divisors of any whole number, and recognize the fundamental theorem of arithmetic. All right, so let's talk about what prime and composite numbers are. All right, one method used in elementary schools to determine the positive factors of a non-zero whole number is to use squares of paper or cubes to represent the number as a rectangle. Like here, the following rectangles represent the number 18. So let me go ahead and pull this up. All right, so here we got one long row of 18 blocks. That would be one row times 18. So 1 times 18 is a way of representing the number 18. Or 2 rows with 9 squares in each row. That would be 2 times 9. Or 3 rows with 6 squares in each row. That would be like 3 times 6. So the number 18 has 6 positive divisors. 1, 2, 3, 6, 9, and 18. Okay. Now, below each number listed across the top, we identify numbers less than or equal to 37 that have that number of positive divisors. Okay. So here is that table right there, and it's up to 37. Okay. Now on the next page, we're going to focus on this column right here, where the 2 is. That's 2 positive divisors. That means that these numbers that you see in this column under the number 2 have exactly 2 positive divisors, 1 and the number themselves. Okay. That will have a special name, which we're going to talk about shortly. And then the one in the middle, this one, from 3 on up to 9, those are the numbers that have at least 1 factor other than 1 in themselves. Okay, so they have more than 2 positive divisors. And then the figure at the bottom only shows the number 1 with only 1 positive divisor. So here it is neither prime nor composite. Okay, so this right here is what introduces 2 types of numbers: prime numbers and composite numbers. And here are their definitions. A prime number is any positive integer with exactly 2 distinct positive divisors. Okay, so the column that I just showed you here, that column right here only has 2. These are the numbers that only have 2 positive divisors. Now, this is only up to 37, but there are more prime numbers here. And then composite numbers are going to be any integer greater than 1 that has a positive factor other than 1 in itself. So here in this case, these right here have more than 2 positive divisors. Okay, like the number 18 has, in this case, 6 positive divisors, as you can see here. There's 1, 2, 3, 6, 9, and 18. So, excuse me, in this example here, we want to show that the following numbers are composite. Like the number 1564. It is composite because of the fact that I know 1564 has to be divisible by 2, as an example. Okay, so this is composite. And that's because I can take 2 and divide 1564. Now I get a number with a 0 remainder. Part B, 2,781. This will be a composite number because of the fact if I take the sum of these digits in 2,781, this will give us, this will be 9, 17, 18. And 18 is divisible by 3. Okay, if you recall when we were doing the divisibility test here for 3, you have to take the sum of the digits in that number. That sum has to be divisible by 3. And in this case, it is composite. All right, 1,001. And this might be hard to see, but it is composite because, and this is because of the fact that 11 divides 1,001. If you recall when you did the divisibility test for 11, I add the first and the third number, add every other number, every other digit in that number, 1 and 0, that's going to be 1. And then, yeah, well, 1 plus 0, that's going to be 1. And then add the other digit, 0 plus 1. That's 1. And then 1 minus 1 is 0, and 0 is divisible by 11. So 1,001 is a composite number. And for 3 times 5 times 7 times 10 times 11 times 13, this will be composite as well. Because if you think of this, 3 times 5 times 7 times 11 times 13, whatever this is going to be an odd number. And then I'm going to add 1 to that odd number. That's going to end up being an even number. So even numbers in this case will be composite. Okay. All right, next we'll look at is the sieve of Eratosthenes. The sieve of Eratosthenes. Okay. One way to find all the primes less than a given number is to use the sieve of Eratosthenes. And that's going to be this. If all the whole numbers greater than 1 are considered or placed in the sieve, the numbers that are not prime are methodically crossed out or dropped through the holes in that sieve. The remaining numbers will be prime. So pretty much you're going to be sifting out those composite numbers, and what you'll have left is the prime numbers. Okay. Now on the next page is how we're going to identify our prime and composite numbers. Okay. Now the sieve of Eratosthenes is an ancient method for finding all prime numbers up to a specified number. It was created by Eratosthenes, an ancient Greek mathematician. Just as a sieve is a strainer for draining spaghetti, Eratosthenes' sieve drains out the composite numbers and leaves only the prime numbers behind. So here the numbers 1 to 100 are listed in this table below, and we will use the sieve of Eratosthenes to find all the primes up to the number 100. And we're going to follow these directions here that's given on this handout. All right, first of all, you're going to cross out the number 1. And the reason for that is 1 is not prime, nor is it composite. So we're going to cross out number 1. Second step, circle the number 2. Okay, that's going to be the smallest prime number. And then you're going to cross out every multiple of 2. Well, multiples of 2 will end in either 0, 2, 4, 6, or 8. So I'm going to cross out columns where the numbers end in either a 2, a 4, a 6, or an 8, or 0. Well, take a look at this column right here. They all ended, you have numbers that end in 2, so these can be crossed out. Also, numbers that end in 4, that's divisible by 2 as well. We can cross that out. And then look at this column. They all end in 6. That's also divisible by 2, so we can cross out that column altogether. And then the 8, these all end in 8 in this column, so we can cross that out because 8 is divisible by 2. And then finally, these numbers end in 0. That's divisible by 2 as well, so we can cross those out. So pretty much we crossed out just about half of the numbers in this table. Okay. So that's pretty much half the table, half the numbers here that are gone. And then the next open number will be 3. So here we're going to circle the 3. And I'm going to cross out every multiple of 3. Okay, so that means the 6 is already gone. 9 is a multiple of 3. We can cross that out. 12 is already gone. 15 is a multiple of 3. We can cross that out. 18 is a multiple of 3. That's already gone. 21 is a multiple of 3. Cross that out. Then 24, 27. Cross that out. Then 30. And then 33 can be crossed out. 36 is already gone. 39, we can cross that out. And then, let's see, 42 is gone. 45, we can cross that out. 48, 51 can be crossed out. 54 is already gone. 57 can be crossed out. 60 is gone. 63 can be crossed out. 66 is gone. 69 can be crossed out. That's a multiple of 3. 72 is already crossed out. We can cross out 75 because that's a multiple of 3. 78 is gone. 81 can be crossed out. 84 is already gone. 87 can be crossed out. 90 is already gone. 93 can be crossed out. 96 is already gone, and 99, we can cross that out. So those are the remaining multiples of 3. Now let's circle the next open number, which is in this case 5. So we cross out every multiple of 5. Well, any number that ends in a 5 or a 0 we cross out. Notice this last column right here, ends in 0. Those numbers are already crossed out. But for the 5, any number that ends in 5, we can eliminate those. So we can eliminate these numbers in this column. And then we circle the next open number, which is 7. And we eliminate every multiple of 7. Let's see. 7, and then, well, 14 is gone. 21 is gone. 28 is already gone. 35 is gone. 42 is already gone. 49, we can cross that out. And then 56 is already gone. 63 is already gone. 70 is already gone. 77 is a multiple of 7. We can cross that out. 84 is already gone. Plus 7, 91, we can cross that out. 98 is already gone. Okay. All right, and then we continue the process until all the numbers in the table have been circled out. So the next open number will be 11. Okay, and then we cross out all the multiples of 11, which is in this case, those with double digits. And guess what? They're already gone. So pretty much we can go ahead and circle the remaining numbers like 13, 17, 19, 23, 29, 31, 37, 41, 43, 47, 53, 59, 61, 67, 71, 73, 79, 83, 89, and 97. So these numbers that I have circled represent the prime numbers from 1 to 100. Okay. And all the other numbers that I've crossed out are composite numbers. Okay. So do be familiar with your prime numbers here, because we're going to be dealing with these when we do what they call the prime factorization. So that's going to be the next thing we'll talk about here, the prime factorization. Composite numbers can be expressed as products of two or more whole numbers greater than 1. And each expression of a number as a product of factors is a factorization. But if you have a factorization that contains only prime numbers, then we call that a prime factorization. Okay. Now, next is the fundamental theorem of arithmetic, which is another name for it would be the unique factorization theorem. And the unique factorization theorem is this: each composite number can be written as a product of primes in one and only one way, except for the order of the prime factors in the product. And to find the prime factorization of a composite number, you're going to rewrite the number as a product of two smaller natural numbers. If the smaller numbers are prime, you're finished. If either is not prime, then you're going to rewrite it as a product of smaller natural numbers. And then you're going to continue until all the factors are prime. So let's look at these two examples here. Here we have a prime factorization for 84 and for 495. Starting with the 84, what they did was they came up with two numbers that are a product of 84, which will be 4 and 21, because 4 times 21 does give us 84. Well, 4 is not prime and 21 is not prime. So we can write 24 as 2 times 2. And also 21 can be written as 3 times 7. 2, 3, and 7 are prime. So 84 would be 2 times 2 times 3 times 7. But 2 times 2 can be written as 2 to the second, then times 3 times 7. And for 495, in this case here, they found two numbers multiplied together to give 495. Here they use 5 because this number ends in 5. So 5 times what number gives me 495 has to be 99. And here 5 is prime, but 99, we can write that as a product of two numbers. 11 times 9. Here, 11 is a prime number. We can write 9 as 3 times 3. 3 is prime, and 3 is also prime. So here is the prime factorization of 495. 3 times 3, or 3 to the second, times 5 times 11. Now, in the middle of this page, you'll see the two trees producing the same prime factorization, except for the order in which the primes appear in the products, like 260. Well, 260 is a multiple of 10, so they broke that up as 26 times 10. And then 26 is a composite number. We can break that up as 2 times 13. 2 is prime, 13 is prime. The 10 can be broken up as 2 times 5. 2 is prime, 5 is prime. Now, another way of breaking up 260 is this. Since 260 is a multiple of 5, we'll do 5 times what number gives me 260? And that would be 52. And then 52 can be broken up, since we'll start with 2, since 52 is an even number. 2 goes into 52 26 times, so that's 2 times 26, and 2 is prime. And then 26 can be broken up as 2 times 13. So as you can see, you get the same prime factorization. The only difference here, with the exception, is the order in which the primes appear in the products. All right, now let's look at this first homework example. Let's say I want to find the prime factorization of 2,205. Prime factorization of 2,205. Now I'm going to start off with a number that I know is divisible by 2, that 2,205 is divisible by. Let's start with the 5, because 2205 ends in 5. And now we're going to divide 5 into 2,205, which will be 441. And 5 is a prime number, so what I would do is circle the 5, since it is prime. Now for 441, we're not going to be able to use 2 because 441 is not an even number. Let's try 3. So 441 divided by 3 does give us 147. And 3 is prime, so we're going to circle the 3. And now for the 147, well, it's not divisible by 2. Let's try 3. Okay, so here, 3 goes into 147, 49 times. 3 is prime, so we'll circle the 3. And I know 49 can be broken up as 7 times 7. 7 is prime, so I'll circle the 7s. So the numbers that I have circled are represent the prime factorization of 2,205. And let's try to put this in numerical order. I got 2 3s as a factor, so this will be 3 to the second times the 5 times, and 7 is used as a factor twice, so it'll be 7 squared. So this represents the prime factorization of 2,205. 3 squared times 5 times 7 squared. Okay. All right, let's look at this example that's in the homework. Fill in the missing numbers in the factor tree. And part B, how can you find the top number without finding the other 2 numbers? All right, so let's start from the bottom here. If I have 3 times 7, I can find that out. It would be 21. Excuse me. And then to find this number, I got 2 times 21. I can multiply that. It'll be 42. And then I can multiply the 5 times 2. That would give me 210. Okay. So I've completed that factor tree. Now that's part A. Now in part B, how could you find the top number without finding the other two numbers? Well, here's what I can do here. I can multiply the 7 times 3 times 2 times 5. Well, if I do 7 times 3, that would be 21. And then 21 times 2 would be 42. 42 times 5 gives me the 210. So I can just multiply these numbers on the bottom to get the 210. Okay. All right, here's another homework example. Let's say I want to find the prime factorization of each of the following numbers. Like in this case here, let's start with part A. 55 to the 5th times 65 to the 23rd times 49 to the 11th. All right, I'm going to break 55 up as a product of prime numbers. That's 5 times 55, 5 times 11. 5 is prime and 11 is prime, so that'd be 5 times 11 raised to the 5th power. Times that 65 is 13 times 5. 13 and 5 are prime, so this would be to the 23rd power, times, now 49 would just be 7 times 7, and that's raised to the 11th power. Now I'm going to be using the rules for exponents here that I did talk about back in chapter 3. Okay, if you raise a product of two numbers to a power, each factor will be to that exponent on the outside. So that 5 will be to the 5th power, times the 11th will be to the 5th power, times the 13 will be to the 23rd power, and the 5 will be to the 23rd power as well. And then what's in the parentheses will be to the 11th power. So the 7 will be to the 11th, and 7th will be to the 11th power. All right, now let's think about this. We're going to use the product rule for exponents. Anytime you multiply powers of the same base, you bring over your base and add your exponents. Like, I'm going to group this. 5 to the 5th times 5 to the 23rd times 11 to the 5th times 13 to the 23rd times 7 to the 11th times again 7 to the 11th. Here, if I multiply powers of the same base here, 5 to the 5th times 5 to the 23rd, bring down the common base of 5 and then add 5 and 23 together, you'll get 28. Can't do anything with the 11 to the 5th, so I bring that down. I can't do anything to the 13 to the 23rd, I'll bring that down. But here, 7 to the 11th times 7 to the 11th. Multiplying powers of the same base, bring over the 7, add your exponents. 11 plus 11, that's 22. So this ends up being 5 to the 28 times 11 to the 5th times 13 to the 23rd times 7 to the 22nd. Okay, part B. 500 raised to the 40 times 1800 raised to the 37. All right, so now I'm going to use some scratch paper here. That 500, I can write that as, well, let's say 5 times 100. And then 100 will be 10 times 10. And 5 is prime, so I'm circling the 5. 100 is 10 times 10. 10, I can break that up as 5 times 2. This 10, also 5 times 2. 5 and 2 are prime. So 500 would be 5 to the 1, 2, 3 power times 2 to the second power. So I'm going to write 500 as this. 5 times, well, 5 to the third times 5 to the third times 2 squared raised to the 40th, and then times, now for the 1800, let's see, 1800 would be 18 times 100. 18, I can break that up as 9 times 2, with 2 being prime, and 9 would be 3 times 3, with 3 being prime. 100 is 10 times 10, and 10, each of the 10s will be 5 times 2. So 1800 will be, in this case, 2 to the third times 1, 2, 5 to the second times 3 squared. Two cubed times 5 squared times 3 squared, and that's raised to the 37th power. Okay. So what's in the parentheses, the numbers in the parentheses will be to the 40th power. And if you're raising a power to a power, you're going to multiply your exponents here. So in this case here, 5 to the 3 times 40 would be 120 times 2 raised to the 2 times 40, that would be 80, times, now 2 to the third to the 37, bring down the 2, multiply 3 times 37, that would be 111, and then 5 to the 2 times 37, that would be 74, and then 3 to the 2 times 37 would be 74. And now when we're multiplying powers of the same base, we always add the exponent. So dealing with the 5 to the 120 and 5 to the 74, bring the 5 down and add 120 and 74 together, you'll get 194. So it'd be 5 to the 194th power times 2 to the 80th times 2 to the 111. That'd be 2 to the 191, and then times 3 to the 74th power. So that's how you do part B. All right, now part C. And this one is different. We got 2 times 3 to the 4th times 5 to the 110 times 7 plus 4 times 3 to the 4th times 5 to the 110th power. Okay. Let's do this. I'm going to tackle this part right here. I'm going to go ahead and multiply, in this case, 2 times 7. I know that's going to be 14. I tell you what, I'm going to omit this problem right here. Okay, I'm going to omit that particular problem. Now for part D will be 2 times 3 times 5 plus 1. 2 times 3, that'll be 6. 6 times 5 will be 30. 30 plus 1 will be 31. And if you were to do the prime factorization for that, it'll just be 31 because 31 is a prime number. Okay. Okay, I'm going to omit part C. And if I'm able to do that particular problem, I will do another video just for this particular problem in the homework example number 5. Okay. We can also determine the prime factorization by dividing with the least prime 2, if possible. If not, we try the next larger prime as a divisor. And once we find a prime that divides the number, we continue by finding small primes that divides that quotient, and so on. Like for 260, we start off with 2. 2 goes into 260 130 times, and then we try 2 again. Since 130 is an even number, 2 goes into 130 65 times. Now, 65 is not an even number, but I know it ends in 5, so let's try the 5. Try dividing 5 into 65, that goes 13 times. And then, of course, 13 is a prime number. We can divide 13 each to itself, that goes 1 times. So the numbers on the left side represent the prime factorization of 260. All right, now we'll talk about the number of whole number divisors. Number of whole number divisors. So let's try to ask ourselves this question. How many positive divisors does the number 24 have? We're not asking how many prime divisors, just a number of divisors, and it can be any divisors, okay? So these are all the factors of 24. And sometimes I like to list them in pairs, like 1 and 24, 2 and 12, 3 and 8, 4 and 6. Okay. And since 1 is a divisor of 24, then 24 divided by 1 is equal to 24 will be a divisor of 24. And 2 is a divisor of 24. 24 divided by 2 will be 12. That's a divisor of 24. And so on. Okay. Which leads to this theorem. If D is a divisor of N, where N is not equal to 0, then N over D is also a divisor of N. Now, another way to think of the number of positive divisors of 24 is to consider the prime factorization of 24, like this. 24 breaks up as 2 to the 3rd times 3. That's just, start doing the factor tree if you like. And then 2 to the 3rd is equal to 8. It has 4 divisors, and the 3 has 2 divisors. And then using the fundamental counting principle, there are 4 times 2, which is 8 divisors of 24. Now, on the next page, you'll see the positive divisors of 2 to the 3rd and 3 to the 1st. And then, of course, the positive divisors of 3 to the 1 and 2 to the 3rd. There you see them all listed out. For 2 to the 3rd, there are 1, 2, 3, 4 positive divisors. For 3 to the 1st, there are 1, 2 positive divisors. Combine those two, it's a total of 8 positive divisors. So this leads to this particular rule. If P and Q are different primes, M and N are whole numbers, then P to the N times Q to the M has N plus 1 times M plus 1 positive divisors. Okay. So let's look at a couple of examples of this. Let's say I want to find the number of positive divisors for 1 million. Okay. And we need to find the prime factorization of 1 million. which is, of course, now I'm going to write 1 million. As 10 to the 6th. Reason for that, because I know 1 million is a power of 10, is a multiple of 10. So I can write that as 10 raised to the 6th power because it has 6 zeros in 1 million. And of course, 10 is 2 times 5 as a prime factorization. And of course, 2 and 5 will each be raised to the 6th power. So 2 will be to the 6th power times 5 would be to the 6th power. And using this particular theorem that I have up here, this rule, in this case, I have 6 plus 1 times 6 plus 1, taking each exponent, adding 1 to each of them. So this 6 will be 6 plus 1, and this 6 here will be 6 plus 1 because of this rule, n plus 1 times m plus 1, positive divisors. Well, 6 plus 1 is 7. 6 plus 1 is also 7. So 7 times 7 is 49. So there are 49 positive divisors in the number 1 million. Another example would be to find the number of positive divisors of 210 raised to the 10th power. Well, let's write 210 as a prime factorization. I'll write that as 21 times 10, since it ends in 0. 21 is 3 times 7. 10 is 5 times 2, and all of these are prime numbers. So 210 raised to the 10th would be 3 times, 7 times, 5 times 2, all raised to the 10th power. So every factor in the parentheses will be to the 10th power. That means 3 will be to the 10th power, 7 will be to the 10th power, 5 will be to the 10th power, and 2 will be to the 10th power. Okay. So let's look at what we have here. Each of these will add 1 to it. So it'll be 10 plus 1 times another 10 plus 1 times another 10 plus 1 times 10 plus 1. Well, 10 plus 1, that's 11 times 11 times 11 times 11. That ends up being 11 to the 4th. And if we simplified 11 to the 4th, this will be 14,641. So 2 to the 10th raised to the 10th has 14,641 positive divisors. Okay. All right, next we'll look at determining if a number is prime. All right, to determine if a number is prime, you must check only divisibility by prime numbers less than the given number. For example, to determine if 97 is prime, you must try dividing 97 by the prime numbers 2, 3, 5, and so on, as long as the prime is less than 97. If none of these primes divide 97, that means that 97 will be prime. And upon checking, if you were to do 97 divided by each one of those, you'll see that 2, 3, 5, and 7 do not divide 97. That means 97 is a prime number. And here's a theorem that we're going to be using to determine the greatest prime that we must consider to determine whether a given number is prime. If n is a composite number, if n is composite, then n has a prime factor of p such that p squared is less than or equal to n. Okay. And also another theorem says here, if n is an integer greater than 1 and not divisible by any prime p such that p squared is less than or equal to n, then n is a prime number. So let me simplify that p squared less than or equal to n. If I take the square root on both sides of this, that would mean that p would be less than or equal to the square root of n. Okay, so whatever that number is, we'll take a square root of that, and that will tell us what would be the largest prime that we can test, that we can consider. So let's look at this example here. We want to tell whether the number 117 is prime using this. So here your n is 117. So here p is less than or equal to the square root of n. So substitute your n with 17. So here p is less than or equal to the square root of 117. And if you take the square root of 117, put this chunk out. There's a square root key on this calculator, trust me on that. And then 117. In this case here, you're going to get 10.8. But the largest prime number that we can test, if you recall, they have to know what your prime numbers are. The primes have to be, that we can test will have to be less than 8. I mean 10.8. In this case, it has to be less than 7. Because we can test only 2, 3, 5, 7. Not 11, because 10.11 is more than 10.8. Okay. So our primes that we can test will have to be 2, 3, 5, and 7. And if you get a whole number, that tells you that that number is a composite number. So if I do 117 divided by 2, I'm going to get a decimal of 58.5. Let's try 117 divided by 3. Here we get a whole number of 39. So that means 117 is actually not a prime number. It's actually composite. So here 117 is composite. That is because 3 does divide 117. All right, now let's look at this example. What is the greatest prime you must consider to test whether 5089 is prime? So here I'm going to use that p is less than or equal to the square root of n. And I'm going to let n be 5089. So I take the square root of 5089. If I take the square root of that, I get 71.333. So the largest prime that I need to consider will have to be based on this 71. The prime has to be less than 71.3, so the largest prime is 71. Okay. Okay. On the next page is 397 composite or prime. So let's use that p is less than or equal to the square root of n. And then take the square root of 397. So square root 397. That'd be 19.9. So the largest prime I need to consider that I can use would be 19. So I can't go no further than 19. I can test these prime numbers 2, 3, 5, 7, 11, 13, 17, and 19. Well, no, 397 is not divisible by 2 because it ends in a 7 is not an even number. Let me try 397 divided by 3. And I'll tell you, I'm going to get a decimal with that one, so that's out. 397 is not divisible by 5 because it doesn't end in 5 or 0, so that's out. 397 divided by 7 gives me a decimal. 11 divided by 397 would not work either, so that's out. 397 divided by 13. That gives me a decimal again. 397 divided by 17 also would not work. And 397 divided by 19 would not work as well. So those primes do not work. So this means that 397 is prime. Let's try 91. Is 91 prime or composite? Okay, so here we do p is less than or equal to the square root of n, and n will be 91. So if I take the square root of 91 on the calculator, this will be 9.5. So the largest prime numbers I can test will have to be less than 9.5. So it has to be 2, 3, 5, and 7. Now, if I divide 2 into 91, or 91 divided by 2, that's going to give me a decimal of 45.5. So I could eliminate that. Let's see, 91 divided by 3. Let's try that. We can eliminate that as well, because that will give me a decimal. Of course, 91 divided by 5, well, I already know this does not end in a 5 or a 0, so that's out. 91 divided by 7 would be 13. Okay, because at 7, I get a 0 remainder. So that means that 91 is composite. Reason for that would be that 7 does divide 91. Okay. And let's look at these last 3. Identify each number as prime or composite or neither. All right, let's take a look at number 30, the 30. The number 30 is composite because I can break 30 up as 5 times 6. Now 53, now this is in your sieve of Eratosthenes. And this is important for you to understand and remember your prime numbers. Here 53 we circled as a prime number. So that means 53 is prime. And we talked about this one before, the number 1. Okay, the number 1 is neither prime nor composite. Okay. Pretty much, if you look back here, we did talk about this earlier, where the number 1 has only one positive factor. It is neither prime nor composite. So the number 1 is neither prime nor composite. All right, so that does conclude this video on section 4.2, dealing with prime and composite numbers. Do feel free to email me if you have any questions about anything presented in this video or the homework in my math lab.